change in the program, so we will have Tom also today, and then we will have an overdose by Antonello for 3 days in a row. So let's start.
Yeah, right. Okay, perfect. Okay, yeah. Hi, everybody. Long time no see. As you know, we talked about quantum antibody scars last time, and today I'm going to talk about Hilbert space fragmentation. But before we move on, I wanted to tie up a couple of loose ends from last time. The first is, of course, this typo, which kept me from, perfect score. So this is the correct equation. But the important thing that I wanted to also point out, which is, we talked a little bit about how when you put magnons on top of a state, they scatter, right? And Eduardo reminded me or sent me a very nice paper from Physical Review 1965, where they do a very careful calculation of the two magnon scattering. And if you do this problem, like, you have plane wave solutions, which are fine, like no problem. And then you try to put two plane wave, like two magnons both in a plane wave, then it turns out that you can almost rewrite it as two plane waves, except there's an extra term that generates the scattering. And what is that term? It's actually precisely this guy acting on the vacuum. So demanding, this basically just gives like another like physical perspective on this thing, this theorem, which is that if J plus is interpreted as producing an excitation on top of the vacuum, then demanding that this thing vanish as an operator is essentially saying that at the momentum where these excitations are created, suppose 0 or pi, then the scattering is just forbidden. And then it's kind of intuitively obvious that you can put as many of these things in as you want until you fill up the system. So I just wanted to make that point because I think it's a nice connection between this and the earlier discussion. So good. And then I think towards the end of last lecture, used the term weird conserved quantities. And this was specifically in reference to so we know, for example, that this J plus here, right? It is not the case that the commutator of H with J plus is equal to omega times J plus as an operator. That's not true, right? But if you wanted to, you could produce a projection operator out of these guys that I called P scar, right? And then if you dressed this thing with the P scar, then it would be a conserved, it would be a symmetry, right? But this is kind of a strange operator because, I mean, I don't know how many talks you've been to on like eigenstate thermalization and whatever, but you've at least been to a couple now. But, one of the things that you talk about sometimes there is that, when you try to distinguish, like, what is integrability versus like, non-integrability, like every Hamiltonian has exponentially many conserved quantities, but they're like projectors on the eigenstates, and somehow that's not a conserved quantity that we typically think of as being like meaningful in the sense that like you don't resolve it when you do ED because resolving it requires you to know all the eigenstates. So this is like a little bit, I would say this is like one notch kind of below that, on the spectrum between like regular locally generated symmetries and eigenstate projectors. This is like, a projector onto a sort of low entanglement subspace of eigenstates. And scars are sort of an example where, you do get this thing. And then if you look at the Hamiltonian of a model with scars and you sort of resolve this symmetry, then you basically like, you can kind of diagonalize in this sector, and then you have a fully connected sector over here. And you just split your model into two subspaces.
You totally kill the both diagonals.
Between them, yeah, because this is basically just representing that there's these special, there's a special subspace that's decoupled from everything else. Yeah, exactly. Okay, so now what I want to do is kind of like pass from this, which is already strange, right, to something which is stranger, which is Hilbert space fragmentation, which is again like it's you have again some weird conserved quantities, but you have more of them potentially, and I should, you know. There were like a couple of papers on this in 2020 or 2019, so. But the phenomenon is known and has been known for a long time just because like anybody who's done like Monte Carlo, right? Sometimes your Monte Carlo dynamics is like not fully ergodic. It's ergodic within some manifold of states, but then there's some other states somewhere that you can't reach. So this is kind of an example of this. So let me try to explain what I drew here. So, you know, normally like if you have a Hamiltonian that has some symmetries, you can block diagonalize it by resolving the symmetries, right? So these blue blocks are kind of what you would get if you just had like a Hamiltonian with, you know, magnetization conservation, and then these would be the sectors of different magnetization. So in this like Hilbert space fragmentation, what happens is that within these things that I would call conventional symmetry sectors, so these would be like normal kind of locally generated symmetries, you have further decomposition into these diagonal, or further block diagonalization is possible, basically. So these symmetry sectors kind of break up into these little sectors that people call sometimes fragments or Krylov sectors. Now, why do they call them Krylov sectors? Well, it just has to do with the concept of Krylov subspace methods, which are numerical techniques. And it's basically where you generate a subspace that's smaller than your full Hilbert space to diagonalize your problem or represent your time evolution or something. And this subspace is just the span of powers of your Hamiltonian acting on some sort of simple state. So these sectors are basically, you know, if you took the Hamiltonian and you applied it many times, you would never be able to get out of this little part of Hilbert space, no matter how many times you apply H. And then, of course, that implies when you do dynamics, right, e to the minus IHT, you get all powers of H, but it doesn't matter how many powers you have, you'll never get out, right? So that's what Hilbert space fragmentation is. It's basically, you know, your Hamiltonian further block diagonalizing even after you've resolved like, or after you think you've resolved all of the basic symmetries of your problem. Yeah. Yeah, so this is usually like a product state, or, you know, maybe you want to get fancy and you do like, you know, Hartree-Fock mean field or something, and then you do some extra I mean, yeah, you just take some state that you know how to produce easily on a computer. In this case, psi 0, like, you know, you could take any product state kind of in this part of your Hilbert space, basically. Yeah.
Are there ways of identifying the number of Krylov sectors you will have in any conventional symmetry sector?
Yeah, so this is a very good question. I mean, you know, without doing, you know, basically representing. Yeah, so like, you know, what you can do, for example, and then this keeps me moving along, which is great. So you can make a Fock space graph, which I believe you're familiar with, and I believe you're familiar with, and probably you are familiar with by now if you went to the talks. So, you know, what you do is you know, if you want to see this structure, you can basically, you know, say project into a magnetization sector and then just look at what your Hamiltonian looks like. And your Hamiltonian, you know, even if it's quite complicated, you can always turn it into the adjacency matrix of some graph. So by that, what I mean is like you can take your Hamiltonian and from that make a matrix which is has ones in it if the Hamiltonian has a non-zero matrix element there, and it has 0 otherwise. And then this basically produces a graph. And then what you find is that this graph And now I'm going to, again, we've established that this is very challenging for me, right? So I'm just going to do my best here. So I'll give you some examples of things that you can get. Okay. So, so basically then what you see is like, basically you want to count the connected components of this graph. So you don't have to diagonalize the Hamiltonian. You just need to be able to put it on your computer. And then, in some cases I'll discuss today, for example, a case where if you put it on your computer, you can find a pattern, and then you can see basically at any system size what the Krylov spaces are going to be, and you can even count them and blah, blah, blah. Good. So yeah, this is going to look a little satanic. I apologize. But okay, good. So actually, this is whatever. Anyway, so this is an example of a fully connected sector. So 5 states and each one is connected to each other one. Okay, so this is something that you can get. Okay, you can also have things that look like this. So this is like a sparsely connected sector. And then you can also have states that just don't have any dynamics. So these are frozen states. So, and I'm not, when I say that something is fully connected, I don't mean that it's literally like an all-to-all, like a complete graph. I mean that it's a graph where if you follow the edges long enough, you can get to from any node to any other node. So I should probably say what the nodes are. The nodes are basically Fock states. So this would be like, a product state like that. Right, so that's typically people talk about, in the computational basis, this is what your graph looks like. And yeah. Yeah, so this is a little bit of a degenerate example, but it's like, so sparsely connected is like, because sometimes, so like if I had a single magnon sector, and for some reason this was like fully decoupled from everybody else, it would actually kind of look like a single particle hopping, right? The graph actually looks like it's a circle, essentially, right? Because like you start off with a particle here, and then you hit it with the Hamiltonian, and then it goes to a superposition of here and here, and then you go, and then on this thing you can make plane waves, right? Because it's literally, it's literally like if it's a chain with if your physical Hamiltonian is a chain with a particle hopping on it, you can make plane waves. But also this graph is a chain in some abstract space, right? So you can play some of the tricks that you play with like certain Hamiltonians on these graphs and writing down, yeah. Yeah, absolutely. You can have these things. Yeah, and these are all things that people have looked at in various, and we talked about, actually this is something that I have in my notes that I didn't say, but we talked about kinetic constraints last time, like the PXP model is an example of a kinetically constrained model. So typically, these kinds of Hilbert space fragmentation things happen usually like due to kinetic constraints that emerge from some combination of symmetries and also an extra restriction on like spatial locality or something. But then because of that, you can get like some funny looking graphs with bottlenecks and stuff. So what I mean by sparsely connected is something like this, where it's like literally if I had a million dots here, it would just be a circle still. I wouldn't have any extra edges. Exactly. Yeah. So that's what I mean by sparsely connected. Yes, absolutely. Yes. Any other questions? Yeah.
On card or Hilbert space representation, because I understand that the underlying mechanisms are very different, but at the time, like, just a great student numerics.
Yeah.
To actually figure out what's happening. It's just.
Yeah. Right. No. So I mean, this is actually something that like it's a little hard to answer. Like I can give you examples where I know that it's a conventional symmetry. So like an example is like any symmetry that's like locally generated, I say. So an example would be this following. So like U1 symmetry generated by conservation of this thing, right? here, I mean, like it's a sum of local operators, okay? But also like a Z2 symmetry generated by something like this, like flipping all the spins in your Ising model. This looks totally non-local, but you can actually write it as like, you know, modulo like me making dumb mistakes. You can write it as, you know, e to the I pi over 2 times the sum of local stuff. So that's what I mean by kind of locally generated. Because you can use this guy as a generator of rotations, and then this is like a special angle of rotation, right? So these are conventional symmetries. And then, you know, what are these other symmetries? Well, it's kind of like anything that commutes with your Hamiltonian, but then you have to kind of decide where you're going to make the cut, because we just discussed that like eigenstate projectors don't really make a lot of, they're not useful necessarily as symmetries, right? So yeah, I think this the thing about this topic that makes me always very confused is that I don't know, and I'm not sure if other people know like where to draw the line. Yeah, exactly. You said it, not me. You said it, not me. I was trying to think how to avoid using that example, but good. Okay, great. Okay, any other questions? Cool. All right. So, all right. So a little bit more terminology. So that, you know, going back to the question, how many blocks are there, right? So there's something called strong, and this is terminology due to these papers. So strong Hilbert space fragmentation, which is basically the following. So let me write some stuff and then I'll say what the stuff is. Or sorry. So what this means is the Hilbert space dimension of the symmetry sector you're in, then look for the biggest subsector, for example, by making this graph. Divide the dimension of the biggest subsector within that sector by the dimension of the sector. And if you do this as a function of system sizes, for example, in a fixed magnetization sector, if you see that this decays exponentially with system size, then we say that this is strongly fragmented. Now, what does that mean? It basically means that you have exponentially many subsectors, you know, because your biggest subsector is already like a very small, exponentially small fraction of the full volume of states that you have. So this sort of implies that you have exponentially many of them, and exponentially we say means strong fragmentation. But you can also have a situation like, you know, I'll talk about something later where like, you know, you have some graph which is like very connected, right? And again, you know, apologies for making you watch this. But you know, you have like one big sector and then there's like a single frozen state, you know? There's a model where this happens. Actually, there's a lot of models where this happens. For example, any model that conserves U1, we talked about this last time. Actually, you need 2 of them, excuse me. Any model that conserves U1, we said, you know, the maximum and minimum magnetization sectors, they only have one state, and it's, you know, generally a product state. And so those are frozen, right? So this is an example where, but they're, you know, it's a bit of a degenerate example because it's, you know, those are actually the only states in their symmetry sector, right? So it's not really fragmentation, but you can have other examples where, you know, you start with something like this in a sector, and then you add perturbations, and then you're left over with maybe some frozen states, but then everybody else is connected, like say order 1 frozen states. And then you have like one big sector that's all connected. And then we would say that this system is weakly fragmented because there's not exponentially many. Or there's not, well, okay, exponentially many. You can have exponentially many frozen states and then one big guy too, but yeah.
like you have one that is still sub-exponential in dimension,
Yeah.
because then you have an exponential with many frozen states.
Yeah.
That is still strong.
No, that's still weak because it's basically like exponential minus an exponential that's going to zero faster. And then it's kind of like basically, you know, the fraction of the biggest sector accumulates all of the states as you go L to infinity. Yeah. 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 Again, just words, but you know, sometimes useful. Good. So this is what we say by strong Hilbert space fragmentation. Okay. Any questions before now I'm just going to basically show some examples. But yeah.
General graphs, can we say anything about the having weights you're going to find on the nodes of the graph?
It's very model dependent. I mean, Hamming weight is basically magnetization. So if your model has U1 symmetry, that actually just defines a sector of fixed Hamming weight is just a magnetization sector. But you can have all kinds of. We're going to see. I mean, basically, what I'm going to show you some examples of like models where this happens, and then I'm going to show how like within a single model you can get basically all of the dynamic stuff we've talked about so far in this conference. All of those things, which appear mutually exclusive, can happen in the same model, basically. So all of these things can coexist due to this thing. So I'll show examples of that. Okay, so maybe I'll do this. So what are some examples where this happens? So all right. So, you know, this is not, again, not a rule, just an observation. So this is often we get it from the interplay of multiple conservation laws. Plus spatial locality. So I'll talk about what that means. But let me show you as an example here. So one example, which does get discussed in the Kamani paper, is charge plus dipole moment conservation. So there, what charge means is what I wrote before. So so just sum over I of Zi is conserved. And then the dipole moment is sort of like, you know, if this is the total mass, if you like, this is then like the center of mass. So J. So charge and dipole moment.
So somehow similar to what people discuss when they talk about fractals.
Yeah, that's right. So this is an example. So people were studying. So when you conserve both of these things so yeah, this fracton stuff, like, you know, those models are typically in like 3 dimensions, but you can define models in 1 and 2 dimensions with the same symmetries and then ask what are their phases. And you can get funny things like a dipole superfluid or, you know, these kinds of things. So yeah, but you know, it's like, yeah.
The difference with the general case is that in this case, each tiny sector can be labeled by genuine values.
Oh, this is the whole point. So you resolve this guy and you resolve this guy, and still there's exponentially many. Yeah. So okay. So let me talk about like where this comes from. Like how do you get a model like this? So as an example, and this is another observation. So no model in nature exhibits Hilbert space fragmentation. Full stop. Full stop. Okay. So why am I telling you? I mean, I don't know. Why did you come? So yeah, no model. Yeah, and the reason. So basically, what happens is you can have this framework like Hilbert space fragmentation is basically like it's a way of talking about like in reality, in the real world, what actually happens is like it takes you a really long time to get out of this little sector. Okay. So this is an example. So all of these models are going to come from doing perturbation theory in some physically reasonable model. Okay, and then you get a slightly less physically reasonable model, but still fine. So here's an example. So this is particles hopping in a tilted potential. Okay, so a tilted potential would look something like this guy. So H contains a term like, you know, some energy scale delta times the dipole moment. It's basically like, you know, to hop to the right, so this is going to be space. So to hop to the right, I pay sort of an energy delta. Okay, so hopping to the right gets hard, you know, it's like climbing stairs. You know, there's a linear energy price you pay. So I guess if you wanted to be concrete, you could say, let's say that the H is like the 1D XY model. In a tilted potential. Okay, so what does that mean? I mean, you know, I said XY model because that's the simplest model I can think of that conserves magnetization. Okay, fine. So what happens here? Well, you can make delta large. You can make delta very large. Okay, so and then what you get is some effective Hamiltonian. Okay, so so then the question becomes the following. So your delta is going to infinity now. So in this model, U1 is an exact conservation law. I never create or remove particles. And then I can change the dipole moment if I hop a single particle. But if this guy gets big, I can do degenerate perturbation theory, because basically what happens is that if, you know, delta is much bigger than 1, I get some states that are, you know, in the grand scheme of things compared to delta quite close together. So then you can say, all right, what are the rearrangements of particles I can do that preserve the dipole moment? And an example of this is if I have a particle here and a particle here, this guy can hop up, that costs energy delta, but this guy can hop down at the exact same time, and that costs energy minus delta, and then you conserve, right? So then your H effective, you know, if your hopping is, what did I call it? J? Good. So, you know, you do 2 hops, and in your intermediate state, you pay an energy delta. So it's, you know, whatever. And I'm going to actually, if you do this calculation carefully, you can have things like signs and cancellations and blah, blah, blah. So I'm not saying that this is the exact Hamiltonian you get, but like the kind of term that you get is basically, you know, so that, let's say that this is site I. So this would be like, you know, CI, C dagger, I plus 1. And then this is C I minus 1, C dagger I minus 2. Okay, and then you would have like extra terms, including the Hermitian conjugate of this, right? So this is a correlated hopping where this guy hops only if the other guy can hop, because that's the only way to conserve dipole moment, okay? So this model has strong Hilbert space fragmentation. Very good. But I stopped at second order in perturbation theory, right? You can have higher order correlated hopping processes that rearrange particles in a way that preserves the dipole moment. So I could hop pairs of particles like this, right? And I can go to whatever order I want. Ultimately, this is the Hamiltonian. So when I say that it comes from multiple conservation laws and spatial locality, what I mean is higher order terms already lead to weak fragmentation. And I think in this model, if not in this model, then certainly the next one that I'll talk about, it's actually the leading correction, the 4th order correction or whatever the next one is, already makes it weakly fragmented. So basically you end up with one big sector and then exponentially many, but measure 0 frozen states. So that's what I mean when I say, so like, you know, this model is reasonable to write down, but the way that you typically would get it in nature is from something like this. And then what that means is that, if your next correction is like j to the fourth over delta cubed, then you have to wait a time, 1 over that to see the next order processes turn on. So that means that there is a parametrically long time scale where this is your Hamiltonian. And that's typically like, there have been lots of experiments that do this, lots of experiments that do other stuff involving Hilbert space fragmentation, and they could see like states freezing. But it's because the experiment is limited to timescales below when the next order processes turn on. Okay.
What's that for in the
Well, it's local in the sense that it's like,
why the indices that?
yeah, you just want to make sure. I mean, you could also have longer, you could have these guys separated by more distance, for example. Yeah. This is just like the simplest, I mean, dot, dot, dot. I'm just giving one example of a process that preserves.
Same process, just
Yeah, right. That can also, that can happen. No, that's the same, that's the same order. Yeah, it's the same order. But, yeah, okay. Well, I think, wait. Yeah. This is that. Yeah, this is that. Yes. Yeah, not necessarily. Yeah, you can put an interaction. Yes. And then, yeah. Yeah, that's right. So yeah, you can put interactions, and then then you have to be careful with you have to be careful with how you do the perturbation theory, right? So I mean, you got to keep track of and you're also going to get some interaction energy change here, right? Generally, so like, yeah, so it may change how the perturbation theory goes. If somebody handed you this model and then you added interactions to it, it doesn't change the connectivity, right? Yeah.
In this model, the prefactor of this model must depend on the fact that we have interactions, because if we really would have one directed particles, one particle pops down, you can see whether the other particle pops up or not. So you could not write down the correlated popping process without interactions.
Sure. Yeah, no, I think, yeah, that's probably right. So I probably need to have, and then you would have in the prefactor somewhere your interaction. It would be like, whatever, minus u or something. I mean, there would be like a u appearing somewhere in the energy denominator. Yeah, exactly. Yeah, so you could add like a u zi plus 1, for example, right? And then you would pay.
Yeah, about in which regime you're with respect to large data.
Sure. Yeah, right. No, that's also, yeah. Do you want to take u to infinity also? Right. Yeah, those are all things that, and they can affect, like, if you have multiple terms going, you have to be careful, like the form of the effective Hamiltonian you get is going to depend on how you take these limits. So if you crank up u and delta, you might have a different connectivity than if you left u finite and cranked up. Yeah. Right. So, but yeah, then this would probably get you a local thing. Yeah, thanks. That's right. Good. But it is true that if somebody handed you this model and then you added interactions or you added anything diagonal will not change the connectivity. Yeah. Good. Any other questions? Yeah.
The dipole is not there for step 1.
Yeah, that's right. So you could call this like an emergent conserved quantity, and it comes about because your spectrum, if your delta is huge, your spectrum just breaks up into these.
Yeah.
I guess I could draw it. Your many body energy spectrum, right? There's some bandwidth, W, but then there's like a big gap delta to the other one. Yeah. Well, the ions, I'm not sure. Born-Oppenheimer in the sense of like.
There is a fast decay of freedom, which is delta.
Yeah, I mean, yeah, that's right. There's a big energy scale. Yeah. There's a big energy scale and then stuff freezes. Yeah, because of the big energy. Yeah, in that sense, I agree with you. Yeah, absolutely. Yeah, this is one mechanism to get this kind of thing. Yeah, so you would call this like this dipole conservation is like an emergent, you would call it emergent symmetry because of this limit. Yeah. Good. Any other questions before I just show one other example? This one, I have the weakness that I never wrote a paper about this model. I only really understand something if I write a paper, which is, whatever. Sometimes even when I write a paper, I don't understand. Okay, but here's another example, okay? So this is going to be charge plus domain wall conservation. So what does that mean? That means your conserved quantities are mz from before, and now the number of domain walls, which is what? So what I mean is, it's again going to be a spin half chain. So a domain wall is when you have an up spin next to a down spin, or if you prefer, like a 1 next to a 0 in the notation that I was using yesterday. Yeah, when you have that, this ZZ is negative, and then this 1 minus ZZ over 2 is 1. So this operator is counting the number of these domain walls, okay? Now, it's actually cool that we had a talk this morning about gauge theory, because it turns out that the spin model that this comes from is a gauge theory. It's not obvious when you just write it down, but I'll tell you maybe in words how it comes out. So xj minus good, and plus, and then now the thing that's going to be my emergent symmetry with energy scale delta is, adding mz. I guess I should be consistent with my dummies. Okay, good. So mz is this guy. Okay, so what does this do? This might look a little bit funny. So you can think of this as another, if you like, kinetically constrained model, but in this case, the kinetic constraint is actually enforcing conservation of this domain wall number. So what does that mean? It means that suppose I want to flip a spin, okay? So let me put a domain wall in, okay? So, and then, my domain wall is this, right? So suppose that I want to try to flip this spin, okay? Can I flip it? So what this term is telling you is, okay, look at the neighbors, all right? If the neighbors are aligned with each other, then ZZ for them, so ZJ minus 1, ZJ plus 1, is going to be positive. And then X minus this is going to be 0, right? Because this ZZ is positive. On the other hand, so basically flipping this guy would be not allowed, okay? What about here? Well, here the neighbors are opposite each other. So that means, if this is spin or site J, this is J minus 1, this is J plus 1. ZJ minus 1 and ZJ plus 1 are opposite. So the ZZ for them is minus 1. And then they add up instead, okay? So what this allows you to do is basically I can flip this spin, but what did I do when I flipped this spin? I just hopped my domain wall by one site. And actually, if you do, if you study the Ising model, like Kramers-Wanier duality, where X and ZZ get interchanged, what you get is an XY model here. So basically the it becomes like a hopping, it's just a, free hopping model for domain walls. Okay, so this model is actually integrable here. But when you turn on delta, that messes up your Kramers-Wanier because Z becomes non-local. Z becomes a string under Kramers-Wanier. So that becomes basically some super duper non-local interaction in terms of fermions. That would be some strings, that come out. So then you're kind of forced to work in terms of spins, but still you conserve domain walls. Okay. Now I said that this comes from a gauge theory. So remember, Jean-Yves had a cool talk today. It was on Zoom, unfortunately, but nevertheless, in a gauge theory you have fermions maybe or hardcore bosons or whatever that can hop, and then you have spins on the links. And if you hop a fermion, you have to flip a spin, or if you flip a spin, you have to make fermions, like that type of thing. So this model actually comes from Z2 lattice gauge theory in 1 plus 1D. But as Jean-Yves told us, like 1D is special because you can use Gauss's law. Basically, demanding that Gauss's law is satisfied is equivalent to integrating out one of the species of particles, or the gauge bosons. Basically, by looking at a configuration of matter, you can read off the gauge field configuration. So in this case, I think the spins are more closely related to the link degrees of freedom. But it's basically become some funny spin model. And then the actual particles are the domain walls, so the fermions. So basically, this is a gauge invariant kinetic term, and that's why it's kind of funny looking. Where's locality here?
If you have huge domain wall, you still allow this moving of the
Yeah, no. So this is much easier to talk about. So this one I actually can give you the answer to. So because you're anticipating already. Maybe let me write down the effective model, and then I'll answer your question. Okay. But this one I actually know it's a cancellation. There's there's cancellation due to signs, basically. But yeah, so here, what do? I take delta to infinity. So this model, the sort of fundamental symmetry, quote unquote, is domain wall number, which sounds funny, but it's basically saying, okay, fermion number is conserved, which is reasonable, right? So then you take delta to infinity, and then again, I'm going to be a little bit schematic, but I'll write down what the actual answer is later because it's interesting. But the actual thing, yeah, but this sort of cartoon is actually enough to understand what happens. So again, it's lambda squared over delta, followed by, so there's a p j minus 1, j plus 2, xj plus 1, plus yj plus 1. And what is this guy? This is a projector that is basically 1 plus zj minus 1, zj plus 2. So this is a second neighbor projector. Okay. So how do you get this? So basically, okay. So what is this thing telling you? So if you think back to here you could only flip a spin if the outer neighbors were opposite. Now you can only flip-flop if the outer neighbors are the same. Okay, so the type of term that you get from this is basically, or the type of dynamics that you get from this is basically, a hopping term like this, or this. So this would be 0, 1, 0, 0, and 1, 1, 0, 1. These would be okay. But and also like, yeah, so basically isolated zeros and ones can hop, but then as soon as they come next to So something like this, right? So 0, 1, 1, 0, 0, right? If I try to do this, I'm not allowed to do this hop because the outer neighbors are oppositely oriented. Now, why physically is that not allowed? It's because where are my domain walls? They're here and here. But then if I hop this guy, I get 0, 1, 0, 1, 0, and now I have 4 domain walls. Okay, so that's not allowed. Okay.
Sorry, the original model before going to that infinite limit, I wouldn't call it into a space fragment, right? Because
No. Yeah.
it's not.
This is regular. Yeah. You just look in the if you resolve the domain wall number, it's already fully connected. Yeah.
Essentially, it's equivalent to a magnetization
Yeah.
number, so to say, because it's out.
Yeah. Like if you just have like some whatever. I mean, obviously this is integrable, but if you turn on a little delta, yeah, you look. Actually, we found scars in this model. That was when we first studied it. But there, it was like one state out of everybody in that sector. But if you take delta big, then stuff happens. Yeah. Good. All right. So I think it's a good time for a break. But what I'm going to do is answer Yvonne's question first. So, okay. So here's a thing. You know, why? So the way that this process comes about, right, is so suppose I have this guy, right? So here I hop, so I do a lambda, and then I get 0, 1, 1, 0, which is allowed, right? But now I also pay something of order delta because I made my string longer. But that's fine, I just hop again, right? And then 0, 0, 1, 0, okay? But you can also ask, okay, well, why can't I have like a big string of ones and then hop the first one and then hop the last one forward, and then it moves the whole blob of ones, you know? So why can't I take a big blob of ones and move it? And basically, I think if you keep track of the energy denominators, you just, it cancels out. Yeah. But, so for example, like I said, this guy, 1, 1, I can't hop this one off. But then if I go to fourth order, I can hop this whole thing coherently. So basically, the higher order terms here that make this thing weakly fragmented basically unfreeze these blobs of ones. So the longer your blob is, the longer it'll take to start hopping. But eventually, it can start hopping. And you can test this numerically. You can basically do the naive thing where you read off all the coefficients in Schrieffer-Wolff, and then you look at the scaling with the blob size, and it's exactly the power law type thing that you would expect. So, yeah, that's right. It's what you expect. Good. So what I'm going to talk about after our short 10 minutes is so you can basically have so we've learned about like integrability and thermalization and many body scars. So I'm going to give you some examples where all three of these things can kind of coexist within the same model due to Hilbert space fragmentation. So for the rest of today, I'm going to ignore the higher order terms, okay? And I'm just going to say, okay, if this was your model, what would be happening, okay? And we can go through that, okay? Good. Take a break. Any questions before break? I mean, I don't know. Or you can ask me a question at break. Okay, cool. Good.
So, initiative is problem. Yes, yes. It's exactly the opposite. Yeah.
Are we all here?
So, yeah.
Cool. Yeah. Hi, everybody. So yeah, good. So the main thing that I want to say, and then we'll see if I get to part B today, but this is like more representative of the basics of the topic anyway. So I'll give a couple of examples that substantiate this claim. So basically, in these systems with Hilbert space fragmentation, you can have localization, integrability, thermalization, scars, all in the same model. So I'm going to give a couple of examples of this, and then you'll see that it's not crazy that you can get all of these things. So one example is the PXP model, which we already talked about, right? So so far we've only really considered the Krylov sector where you have no two ones next to each other, right? So we basically like say, okay, it's like a configuration like this would just be excluded, right? But that's not what this guy really does. What this guy really does is it conserves the quantity number of pairs, which is sum over I, ni plus 1. It's basically the nearest neighbor term in the Rydberg interaction. So this is actually this is a conserved quantity, right? And then enforcing that conserved quantity, which is like a little bit of a weird one because it's across, it lives on a bond instead of a site, that leads to this effective Hamiltonian, which you can flip a spin that's surrounded by zeros, but then if you have this guy, right, this, yeah, so what I wanted to say is that like in reality, this configuration is not actually frozen, or it's not thrown out, I should say. It's just that this part is frozen. This local part is frozen. So over here, I can flip this spin, no problem, right? So this guy I could flip, and like this spin over here, I could flip. This spin I actually can't flip because it's within it's too close to this frozen block. But basically, what this thing does actually is it like cuts the chain, and actually kind of these spins are fixed here because they're next to a 1. But then everybody else, so really, if I wanted to be a little bit more precise, you just say, okay, this guy is here, and this guy is here, right? And what's happening? Yeah. Yes, that's right. No, that's right. Yeah, that's true. So not only, yeah, there's local, this guy actually has like local conserved quantities, actually. Each of the individual terms actually is preserved. Yeah, that's right.
This is somehow, when you were talking frustration free first, right? This is somehow frustration free in a sense.
Well,
It's concerned each of them.
sort of. Yeah, well, it conserves each of them, but the frustration-free discussion was more like when you have a state that can be, every state in the Fibonacci subspace is annihilated by this, for example. So in that sense, it's kind of a frustration-free thing, but I wouldn't call the model frustration-free. So okay, so the point is that like, if you have, for example, so anytime I have like a region with 2 of these 1-1s, right? I could have a longer thing, right? But like, let's say that I just have a 1-1 here and a 1-1 here, right? And then everybody else is, maybe I'll put a 0 here, but then what do I have here? I have a block of, say, L sites. So this block is active. This block stuff can happen, okay? And it's actually literally, this is an open boundary condition PXP chain of L sites, okay? So this is a silly example, but it's essentially, it is an example of localization in the sense that if I put energy in one side of the system, it can't get past this 1,1. So it just chops your chain up. So it's kind of a silly example. Like if you even put one of these in, you know, so if you really consider infinite temperature transport in this model, it's localized, okay? But what Jean-Yves was talking about this morning was, you know, what happens when you project into the Fibonacci sector. And there they found this super diffusive behavior, which is probably some crossover to diffusive behavior, very slow, right? But what would happen here, like if you had like, if you were doing an infinite temperature average or something, basically your chain would just break up into a bunch of disconnected finite size PXP chains, right? But each of those little finite size PXP chains has scars. Like if you initialize the system in with each PXP chain in the nail state, you would get revivals. They would just be undergoing revivals altogether, but they're a bunch of chains that are disconnected. Okay, so this is kind of a silly example, but you know, essentially, this is an example where you have localization because there's no transport of energy, but you have scars because the system is just chopped up into a bunch of chains, and each of those chains has scars. Okay, so silly example, but you know, an example. Okay, good. Any questions about that? Yeah, so but that's a great point. So the Krylov sectors are defined by a configuration of pairs, right? So if there's no pairs, that's a whole Krylov sector, which is the Fibonacci sector, for example. And then, you know, you can put the pairs anywhere. The positions define a Krylov subspace. Yeah. Okay, good. So that's an example. Then I'm going to do another example, which is we're going to go back to this. Oh, I was trying to do the wrong side of the cap. Oh, yeah, yeah, sorry. Yeah.
So even if you have a periodic boundary conditions chain, you
Yeah.
can have effectively this.
Open boundary condition chains. Yeah, yeah, that's absolutely right. That's yeah. So if the whole chain had open boundary conditions, you put your 1,1s down wherever you want them, and then it's a bunch of finite open boundary condition segments. Yeah.
Like I could just ignore the rest of the Hamiltonian and look at the.
Yeah, I mean, you know, you would, it depends what you want to look at. If all that you're interested in is like what's happening in this region, you don't need to consider, like if you just care about dynamics of Pauli operators in this region, you only need to evolve it in this region. It doesn't matter what's going on outside. But if you care about like the dynamics of like the total magnetization or something of the chain with everybody, then you have to do everybody. Yeah.
The eigenstates are still tensor products.
Of course, yeah, yeah. So you would just get every, yeah.
You simulate just.
You simulate each segment independently and then just add them up. Yep, that's right. Yep. Cool. Any other questions? Okay, great. So the other example is coming from this model again. Oh, by the way, so the connection to lattice gauge theory, there's this nice paper by Borla and collaborators. I think it's from 2020. But they show how you do this mapping. Okay. And then, okay, so the second example is I'll call this the domain wall model. Okay. So the domain wall model has quantum many-body scars. It turns out, and that was why we originally wrote the model down. And then we found out that we weren't the first to write it down, which is great because it's actually better. Right? Because it's not just some, without knowing, like, so, yeah. So like I was telling the story in the break. So I got 2 emails when we posted this paper. One was a gauge theory person who was one of these people telling me this is, by the way, this is lattice gauge theory. And then the other was from a Rydberg person telling me, actually, this is the anti-blockade regime of the Rydberg chain. And then I was like, that's great. It's a real model then. Good. Because I literally, we were just trying to fit, we were like, okay, we did it for spin 1. Can we do it for spin half? And then we were like, well, if the Hamiltonian's that, sure. But then, you know, it's always better actually to study a model that's, you know, people care about. So I do cringe when people like act like our paper was the first model, though. We tried to make it clear, even in the published version, we made it very clear that there were these other contexts where the model appeared. But so very good. So, all right. So there's 2 towers of scars in this one, 2. It's not like the spin 1 XY. There's 2 towers. So the vacua are the same as before, but there's 2 towers. So the one tower is states of the form. So there's some operator Q to the power n acting on the vacuum. And what is Q? Q as an operator is proportional to sum over j minus 1 to the j, pj minus 1 sigma plus j pj plus 1. So this is the same p as the PXP model. It's a projector onto 0. And then sigma plus is the raising operator. And then omega is just 0 to the tensor power L. Okay, so it's just all 0. Good. Then the other one is, there's another operator Q prime. So Q prime is proportional to minus 1 to the j. And then now, so remember that P, the projector onto 0, the sort of orthogonal projector to that is n, the density, right? So n is the projector onto 1. So j minus 1, and then now this is sigma minus j, and j plus 1. And omega prime is all 1s. No, no, it does. And we were really into that stuff at the time. But yeah, that's right. Yeah, we were super into that stuff. But no, this is not that. Okay, cool. All right, so, you know, in the spin 1 XY, we had like all spins down, all spins up, and then there was a tower connecting them. But if you think of this as like domain walls, these states have some interpretation. So what is all 0 and all 1 in terms of domain walls? It's a state with no domain walls. So both of these are vacua for the domain walls. They're just degenerate because of the symmetry. They're not degenerate if you have this term, but whatever. But then you start putting in stuff, and then like, what are these things doing? For example, you know, these guys. So Sn, for example, is the projection into the Fibonacci subspace, because these guys happen to, look, I can only raise a spin if the neighbors are down. And that's actually interesting because we didn't like build a kinetic constraint, this PXP constraint into the model, but it comes out in these states. But they're basically projected Dickey states. If you remember the Dickey states that I wrote down last time, I'm going to go proportional because there's a normalization to worry about when you project, as Yevgeny told us. But yeah, so these guys are basically Dickey states, but you know, for n, you know, this would be for n less than or equal to L over 2. Okay, so these 2 towers terminate in the nail states because the nail states are maximally packed with domain walls. Okay, so these towers connect 0 and one of the nail states, or 1 and one of the nail states, or in certain scenarios, it could be like the cat state made of nail states, and then they're kind of attached. It's a little bit, but that's not important. What is important is that these states, like if you look at them, are basically, remember we had like bimagnons, right? Where we had minuses and then a plus, and it was like a double spin flip. So this is like two bound states of nearest neighbor domain walls, and then you make sort of Dickey states out of these guys, these pairs. Okay, so that's what these guys are. One thing that's interesting is, these states are eigenstates of this term. So no matter how big this term is, these guys are eigenstates, right? So that means that in the limit delta going to infinity, where you get this fragmentation, these guys survive as eigenstates, okay? But the question is, what happens to them? Which Krylov sector do they go to? And for this, I'm going to write down what up to, transcription errors is the exact effective Hamiltonian at leading order for this guy. So when you take delta to infinity and actually do the perturbation theory for real, instead of just like looking and thinking, what you get is the following. So sum over j, and then what I'm going to do, so I'm going to highlight terms that maybe you recognize. So j minus 1, comma j plus 2, and then x j plus 1, y j plus 1. So this thing you recognize, right? But there's this extra z here, which I'll talk about in a sec. And there's also an extra term, which is z I minus j minus 1 zj plus 1. Okay, and then everybody is here. Okay, so when you actually do this, you get something that's not this. Okay, it's a little bit different, but I didn't totally lie to you, because this guy and this guy do not affect the connectivity of the Hilbert space. So all of the off-diagonal matrix elements come from this guy. And then what this does is it applies like a configuration-dependent sign to the matrix element. So it's kind of like, if you think of this guy as some kind of like correlated hopping of domain walls, it can happen with a positive or a negative amplitude depending on the configuration. And then this is some diagonal interaction that shifts the energy of configurations relative to each other. Okay. Good. So now I want to bring back, so we have some stuff that I was drawing here, but maybe let me try to do a better job of drawing it. So let me highlight two allowed processes. Right, or maybe an allowed and a disallowed process. Right, so this process changes the number of domain walls, because this is a pair, and then there's this one here. Who knows what's happening here? But then after that, there's only one. So this term annihilates can annihilate a pair of domain walls. So we don't allow this one. But this one can hop. Okay, so 0, 1, 0, 0. I'm just basically rewriting something from before. But I want to bring this here because what does this look like? So your magnons, you can think of them as particles that have sort of an an excluded volume around them. Like there's a region where like the magnons can't get closer. They can't, you know, this spin flip here has sort of an excluded volume where no extra spin flips can enter. Okay. Yeah, they can't overlap. Yeah, exactly. Because of this conservation law. Now, what that means is that if you start off in a configuration like this, which only has isolated, no, these guys can, the clouds can overlap, sorry. Yeah, no, the clouds can overlap. This is fine. This is totally fine. But the ones can't be right next to each other. And there's a reason that this is interesting or important that I'll mention shortly. But, okay, so think about starting in a configuration like this. This guy is never going to bring the two ones next to each other, okay? Now think about these extra terms and what they mean, okay? So this guy says, okay, if now I'll assume all my magnons are isolated, okay? So this guy says, okay, fine, they can hop, right? But I can only hop if, so let's say, for example, that I'm below half filling, okay? Below half filling so that it's like mostly zeros, okay? Then if I have a 1 and I look at the spin to the left of it, it's going to have a 0 there, okay? So that means that this guy is just going to become a minus, right? If I was above half filling, it will become a plus, okay? And then if you look here, well, for this ZZZ, this guy is always going to be, if I have two 1s here, for example, this guy is always going to be 0, okay? So this is like when my 1s get as close together as possible, the spin between them is always going to be 0. So then this is going to be minus as well, okay? So this is going to become, in this sector, it's like you can ignore this guy, and then there's a plus here, and then you can ignore this guy. So now it's an XXZ model, because this is ZZ, except your 1s can't get closer than one site, and the sort of nearest neighbor ones do have an interaction between them. So this turns out to be integrable. This model is integrable. So there's a paper from 1999. And this is not Carlos Alcaraz.
Was not good, man.
No. Yeah, 2003 he was born. I checked that. It was funny. I typed it into Google. I was looking for the reference. I was like Alcaraz Buriev. I got one of their AI summaries at the top, which is like correct, very correct. I was like Alcaraz and Buriev. I just put that in. And then they were like Alcaraz and Buriev wrote a paper where they studied an XXZ model where the magnons can't get too close together and blah, blah, blah. And I did put a little cutout of this in my notes. There's a picture next to the description of the tennis player, Carlos Alcaraz. Ooh, yeah, so I just thought that that was funny. Yeah, exactly. Yeah, no, that's also true. Yep, that's also true. Yep. So, yeah, there you go. So yeah, this model turns out to be integrable, and you can solve it with the beta ansatz like you do the XXZ model, and the beta ansatz equations look almost identical. So it can be solved in essentially the same way, okay? So in this example, what happens to these scar states is that they go into an integrable Krylov subspace. That's what happens to happen. So these states, weirdly, I guess, because they're eigenstates, are solutions of the beta ansatz equations. They're just very simple ones, which is kind of interesting. Yeah, they have a parent Hamiltonian of which, I mean, you know, they're eigenstates of this Hamiltonian, but there's even an integrable model that they're also eigenstates of. Yeah. So yeah, so we've got scars and integrability in the same model, in the sense that you have scars when this guy is finite. And then when you take delta to infinity, the scars go into a Krylov sector that happens to be integrable. So they're not really scars anymore. Yeah, exactly. Yeah, exactly. No. So there's not scars and integrability really coexisting in the same. But if you think about where everything comes from, they come from the same sort of, origin. Okay, good. So we have integrable Krylov sectors. Does that mean that this model here, or with the stuff restored that I crossed out, is integrable? No. So there's actually a way that you can like enumerate the Krylov sectors for this model. So every Krylov subspace can be generated from root configuration. We called it in the paper. I don't know if that's a good name. That has the following form. So basically, there's a frozen block. And then there's a nail block. So there's a frozen block, and then there's some block with like n magnons. So in the integrable example, the frozen block is all zeros, okay? But in general, we talked about how basically any string of zeros or ones that's longer than, that equal or longer than 2 is going to be frozen. So a frozen block would be something like 0, 0, 1, 1. Something like that. Okay, so this is just some string, and every string of zeros or ones is at least length 2. So these guys can't move, right? They can't move. Can they move?
They can if you're well them with pointers.
Did you read the paper? Good. Excellent. Yeah, no, that's right. So they can move, but they move indirectly. Yeah, but this is kind of, so the frozen block is all zeros for the integrable sector. But then if you start putting these things there and you make your sectors big, it turns out that you can look at level statistics and stuff like that within the Krylov sector and with conventional symmetries resolved, and you get Wigner-Dyson statistics and all of that stuff. You can do dynamics and see that it relaxes to, or see that the diagonal ensemble is consistent with the trace of the operator over the Krylov sector. So it's like it thermalizes within that sector, okay? But you would say, oh, there's a frozen block. So doesn't that mean that it's frozen, But actually these active guys can move around and move stuff. So let me give you an example. And then this is going to be something where probably it's going to take me embarrassingly long. See, I already made a mistake. I want to do it because it's a little bit hard to see what happens, and it's something that I'm still mildly interested in. So I have, say, for example, this guy is a block of ones. And then I have this guy that's mobile, right? So this guy can hop here, here. Then what happens when it gets here? Sorry? Not quite. It's not quite. No. Well, sort of. I guess sort of. It depends. You're using some beautifully allegorical language that I struggle to grasp, I think. but yeah. So in the caveman way of understanding this model, not the poetic way, unfortunately. I mean, good. So okay, good. So I just hopped my one and now I'm here. And then I encounter an issue, which is that I can't move this guy. I can't flip-flop this guy anymore, right? Because I have a 1 and a 0. But I can flip-flop this guy. It's just that now my 1 that was mobile becomes a 0 that's now mobile. So this guy, the way that my allegorical description of this is, you know, he just robbed a bank. He gets here, he puts on a mustache as a disguise, and then he keeps running. That's my, yeah. But I like the Newton's Cradle too because it's thematically appropriate. So good. Yeah, so now this guy can hop again. So now I'm going to draw my arrows underneath because now he's hopping as a 0. He's in disguise. And then he gets here, and then you come to the same situation. So 1, 0, 1, 1, 1, 1. Maybe I'm missing a 1 actually. Yeah, I'm missing a 1. Yeah, this is good. Yeah, I feel like I'm doing a magic trick and I'm trying to keep track of the card that you gave me. But it's really, I'm struggling with spatial awareness and pictorial thinking. So again, I'm in this situation where I'm blocked. My 0 can't hop anymore, but my 1 can hop. So he takes off the mustache and puts on a hat, and then can keep running. Okay. But if you look at what happened in this process, right? So this block moved. The frozen block moved, and then this guy can keep going, and it actually moved by 2 sites. It didn't move by 1 site. And that's actually interesting for reasons that I can probably get to today. That's good. But yeah, so it moves by 2 sites, okay? So what ends up happening is that you get subdiffusive spin transport. With z equals 4 for the experts, and this comes from a nice paper from Hans Singh. I think it was PRL. I'll say it's PRL because it's a good paper. No, I'm like 99% sure it's good. But yeah, so z equals 4. The nice, or one way to think about y is that if you think about a region with some big blocks of 1s and then some isolated ones that are flying around, the 1s can basically, you know, modulo sometimes turning into a 0, they can kind of go wherever they want, but then you have these big blocks of 1s that are kind of slow and they get pushed around. So these guys are kind of getting pushed by these guys that are basically undergoing diffusive transport themselves. So it's like these guys are doing a random walk, but they can only walk when a walker goes by them. So it's kind of like a walk on a walk. And then that's why it's z equals 4 and not 2. Good.
Like in this BXP, like 2 months, do you have, or it's only
Yeah, nothing is so the only thing you can make a whole block that's frozen. That's frozen, but there's no like local region that is frozen. Yeah, if it's only nail, that's right. It'll be frozen because it's fully packed with domain walls. Yeah, but if you have any room for the domain walls to hop, they can hop. Yeah, exactly. Yeah.
And there's a tendency of somehow these big blocks be decomposed into several blocks of the same size, right? Because like you're saying you have this big block of 5 1s,
Mhm.
another one of 1. So once they start interacting, somehow you have now
Yeah,
like a 4 and a 2.
yeah, right.
The 2
There's
is faster.
the
so-
intermediate, yeah, the intermediate part of it is a little bit, yeah. So like the what you can say is basically like if you ignore sites that have a mobile particle on them, the spin configuration is conserved. That's another way of putting it. So what I mean is like take your thing and then delete basically like if you like go through here and then you kind of like read, you ignore this guy and then here you ignore this guy and here you ignore this guy, right? And you only read the sites that are frozen. That thing is conserved. Yeah.
Last two ones, I can call one mobile or zero mobile.
Yeah, I would call, in this case, one mobile, but again, you have to choose. Yeah. You have to choose. So if you wanted to write down a conserved quantity for this that is basically telling you this sort of hidden information that gets scrambled up as this guy goes around, you can do it, but it's like a very non-local, hard to parse operator. But you can write down quantities that kind of know about this, this thing. And those are kind of what label, if you like, you know, the Krylov sectors are kind of labeled by their frozen block and then their global domain wall and charge quantum number. Because it's like you make a frozen block and then you populate with ones to make sure that you're in the sector you are in. Does that make sense? Sort of sense? Okay. Yeah.
So which Hamiltonian is this self-place generation is valid?
So which Hamiltonian? So this is valid for this model. Yeah. So if you start from this model and do your large delta expansion, you get longer and longer range terms, and then at some order, maybe like 10th order or something in perturbation theory, this guy can start to hop. This blob of 5 ones can all hop together. Yeah. Good. Yeah, so what happens basically in these sectors is that they do eventually thermalize, and they, operator O at infinite time averaged in Krylov sector K. You can just write it as basically the projection of the diagonal ensemble into this thing. So alpha equals 1 to the dimension of Krylov sector K, and then it's just the usual E alpha psi 0. This is a psi, not a phi, squared E alpha O E alpha. And in this model, this is the diagonal ensemble, which is always there. But this actually, up to fluctuations, that go down with system size is basically the trace of O times projector onto sector K divided by trace of PK, which is just the dimension of the subspace. So in this model, if you take a generic sector and you do dynamics, you find that the actual late time averages of observables are in pretty close agreement with the sort of quote unquote infinite temperature average in the sector that contains the initial state. Okay. Good. All right. So maybe I'll say something about quantum aspects of this. Okay, everything that I've talked about so far is pretty much classical, like at least the part where it breaks up into sectors. Yeah. Yeah.
It's the same paper when you define this model, or is another?
It's a subsequent, yeah. So the scars is where we quote unquote define, but again, we didn't define the model, but it was like where we did the scars that came first, and then the Hilbert space fragmentation came after. Yeah. Right. But yeah, so like all of this stuff is just like certain bit strings can't turn into other bit strings, and that's all essentially kind of classical. But it's interesting that this kind of, so, so you could say that like, because, I think one natural thing to ask when you see something like this is, can I use this to like encode quantum information in some way, or, something fancy? And like without some extra stuff, you can't really, because this is just like classical information, like what was my frozen block? That information is preserved under dynamics from these initial states in this model. But there's nothing really like particularly quantum about it. So, but there is such a thing as quantum fragmentation. Which was defined in, look who it is again. He's written a lot of good papers. So this one is from 2022. So they wrote a very nice paper about Hilbert space fragmentation and something called commutant algebras, which is a fun thing, but I'm not going to really have the time to explore the whole thing. But one thing that they talked about in this paper is, well, yeah, the fragmentation in the bit string basis is all kind of classical, but can you have fragmentation in like an entangled basis? And then this is quantum fragmentation. And the one example that they thought about was this biquadratic spin chain. So it's a spin 1 model. It's just s dot s squared. This is, I think, integrable. And it has this Reed-Salur symmetry. It's like a special symmetry. And it also, you can show, has quantum fragmentation due to the like structure of this symmetry. But I'm going to do a simpler example, which is basically a trivial example of quantum fragmentation, but it also brings out some other quantum stuff. So let me give an example. Simpler example. So let's consider a system that has U1, and then I'm going to use this funny symbol. So this is read semi-direct product. If you've studied symmetry-protected topological phases, you probably know what that symbol is. But it just means that you have two symmetries and the generators don't commute. That's all that it means. Okay. So the U1 is just generated by our old friend MZ. And the Z2 is generated by flipping all spins. Okay. So you would say this has U1 and charge conjugation symmetry. So an example of a model that does this is, not this one because there's the Z, but the effective model, for example. You'll notice it conserves U1, and also it commutes with flipping all the spins because XX plus YY doesn't care about that, and this projector has two Z's in it. Okay. There's also another example, which is just the regular unconstrained XY model. Okay. So actually, let me talk about the XY model, which does not have fragmentation, but it has kind of an example of the thing that I'll be talking about. So the spin half, because we talked about spin 1. So XX plus YY. I'm not going to put the indices because I don't feel like it. Okay, so this guy doesn't have any fragmentation. It just has conventional symmetry, but it has the thing that I'm going to talk about, which is just, these guys don't commute. Okay, so then there's a question about, like, what does that tell you about this model? Does it tell you anything? And I think it tells you something interesting. So let's talk about it. So you can, for example, see that if you do x, mz, x, you get minus mz. Hopefully that's clear. If I flip all of the spins, I also flip the magnetization, right? Good. So I can write this mz operator in the following way. So, I can write it as a sum of z's, but I can also write it as a sum of projectors. So m equals 1 to L, m pm minus qm. So I'll talk about what this is, plus an extra term that's actually 0 times something I call gamma. So this is just notation. So how many eigenvalues does mz have? It has 2L plus 1 if it's a chain, right? So the 2L is these guys, and the 1 is this guy. So gamma is the projector onto the m equals 0 sector, and P and Q are the projectors onto magnetization plus or minus m. So x PM x is equal to QM. Okay, so let's say PM projects onto positive magnetization and QM projects onto negative magnetization, okay? So there's something interesting here, which is now these aren't Krylov sectors in, really, I mean, they sort of are because everything is a Krylov sector, but like these are conventional symmetry sectors, but they have this property that some of them are paired by the symmetry and some of them are symmetric. Okay, so the m equals 0 sector is symmetric under flipping all spins. But, positive or negative magnetization sectors get exchanged when I flip a spin, okay? So what does this imply? Well, I can define some stuff. So let's define some operators now. xm is xpm plus xqm. And why I'm doing this hopefully becomes clear by the time I finish writing this down. So this guy is this. Zm is pm minus qm. Then there's ym, which is xqm minus xpm. Right? There's a sum and a difference of these things. There's this thing. And then there's the quote unquote identity, which is just PM plus QM. Okay? So this guy is the projector onto a particular pair of sectors that I'm now considering together. This is some kind of object that distinguishes whether the sector has positive or negative magnetization. And then this guy, you can think of it as a big matrix which, it's block off diagonal in the sort of basis that's like got the plus m sector here and the minus m sector here, okay? Now, something that's interesting about these operators and the reason that I called them this, and this is an exercise. I haven't given an exercise in a while. And I haven't changed markers in a while, which is why I need to change now. So exercise, show that these things generate an SU2 algebra, basically. So xm squared equals ym squared equals zm squared equals im. So this is one thing that defines that. You can also show that the non quote unquote identity ones anti-commute pairwise. So xm ym equals 0, etc. And you can show that the commutators are what you expect. So xm y m prime, for example, is equal to delta m prime times 2I zm. Okay. So what that means is that for every, not magnetization sector, but for every pair of sectors that are related by the symmetry, I can define this algebra. Okay. And the operators from one sort of collection of these for a fixed m commute with all the other ones for a fixed M prime, and the reason is just that the projectors are orthogonal, okay? Now, why did I do that? I think I can erase this. So the reason that I did this is because now I can demonstrate that, you know, given an eigenstate of a Hamiltonian with these symmetries. So let's say that I have a state E comma M with energy E and magnetization M. So H E is equal to E EM, and also MZ EM is equal to M EM. So given a state like this, you can prove, I'm not going to, but it's not hard, I promise. So there exists another eigenstate, E, you know, so XM acting on E comma M is an eigenstate of H with the same energy and the opposite magnetization. I'm not saying anything super profound, okay? I'm just saying that if you look at the energy spectrum in sector M and in sector minus M, they're exactly the same. Every single energy level has the exact same energy between the two sectors, okay? That's all that I'm saying, okay? So this is not a new thing, but one thing that's interesting is that anytime you have degeneracy, you can define a logical qubit, okay? So each pair of M not equal to 0 sectors encodes, quote unquote, encodes a qubit. And again, I'm not saying anything fancy. I'm just observing that, you know, what is the qubit? Well, there's, you know, Z eigenstates are basically states of the form sum over E coefficients EM and sum over E some coefficients E minus M. So these are kind of like, if you make, you can make a sort of a block sphere defined by these things. And, you know, the north pole of your block sphere has all superpositions of this form. I can make any superposition of any number of states in the magnetization M sector. And that's the north pole, and this is the south pole. And then there's also like logical X eigenstates, right? Which is what? Well, it's coherent superpositions of these states. So that means they have the same coefficient, but then I have EM plus or minus E minus M over root 2. Okay. Now, okay, these are they're qubits. I mean, you know, it's a little bit like if you've studied like systems with topological order or strong zero modes or something like that, where you have an algebra of operators that guarantees degeneracy, and then any superposition of states with the right combination of eigenvalues you can take to be sort of logical eigenstates. I'm not really doing anything special. You're kind of like, why am I doing this, probably? And that's a good question. But all that I wanted to say with this is that basically these are qubits. There's a few reasons why, you know, maybe we wouldn't really care too much about this. One reason is that like these guys, for example, these are, again, this is just any state within a symmetry sector can be expressed this way because it's a complete basis. But then there's these kind of coherent superpositions of eigenstates which, you know, remain coherent, right? And these are kind of, you know, these are coherent, right? They're nice, they're superpositions. You know, in a sense, this is a little strange because these guys come from different symmetry sectors. They come from sectors with opposite magnetization. So like if your magnetization was actually talking about the number of particles, it's like a superposition of states with two different numbers of particles, which is a little bit unphysical, okay? And also, the invariant sector, m equals 0, doesn't store a qubit. And I'm going to finish up in like 5 minutes or so. So yeah, this doesn't store a qubit, right? But here, if you have Hilbert space fragmentation, all right, now something can happen in here, okay? So I'm going to erase this that I just wrote. So what I'm trying to say is that you can do the exact same thing in the m equals 0 sector when you have Hilbert space fragmentation. And then you can write this gamma in the following way. You can write it as the sum over j equals 1 to k0 of gamma j. And this is like not really with reference to any particular model. It's just with reference to model with this symmetry. J equals 1 to k pi, pj plus qj. So what am I trying to say here? So the total number of Krylov sectors is k equals k0 plus 2 k pi. So k0 is the number of unpaired sectors. And then k pi is the number of pairs of sectors. Okay? So if I look at whatever Krylov spaces I get, subspaces, some of them will be invariant under the symmetry. Oh, man. Some of them will be invariant under X, and some of them will be paired by X. Those are the only two things that can happen if you have a symmetry that is a Z2 symmetry that squares to 1. Okay? So what this means is that within that sector, you're going to have k pi copies of that algebra. So what's going to happen is that I'm going to have paired sectors will have exactly degenerate spectra because of the same algebra, okay? And unpaired sectors will be non-degenerate, okay? So then the thing that's kind of interesting is that, you know, I'm in one conventional symmetry sector that's invariant under both operations, like both U1 and X. But I can make, I essentially have now k pi encoded qubits in one sector. Okay, so this is a little bit like it's a little bit like strong zero modes. So there's some. This is yeah. So there's a nice paper from Paul Fenley that. I mean, he has several papers about zero modes, strong zero modes, but there's this paper from 2016 where he talks about how, you know, you can have these degeneracies over the entire spectrum that come from a many-body zero mode in your Hamiltonian. And those can be things like, you know, edge modes, topological edge modes, and things like that. This is something that's a little bit different. It's just the projectors onto these Krylov sectors, which are, again, some weird symmetry, right? Strong zero modes are also some kind of weird symmetry that comes out in the thermodynamic limit, something that commutes with your Hamiltonian. But it's not something that's a strictly local operator or even locally generated. So all that I wanted to say is that, yes, your Hilbert space breaks up into these sectors, but if you have an extra symmetry around, you can get these degeneracies, and inside of those degenerate subspaces, you can encode some quantum information. So if you think about, and then I'll end on this because I wrote down the theory of everything at the beginning, and it's only fitting to write down one case of it at the end. So I can go e to the minus I ht acting on what? Well, I could act on some coherent superposition of a product state B and its Z2 conjugate. So this state is coherent, but if you didn't have fragmentation, this state would just become some superposition of eigenstates. But if B is in some sector Pj, then XB is in some sector Qj, and then what you get is a sum over energies of some coefficients e to the minus I, Ej t, and then Ej with, positive eigenvalue of this Z operator and Ej with the negative eigenvalue of this Z operator. So what happens in this state is that components, like if you start with a general superposition of states, the components between, the components at different energies will dephase. But then there's degeneracies that don't, where you can't dephase, basically. So there are these degenerate subspaces that can't dephase. And how many of them? Well, there's exponentially many generically, because, for example, in this kinetically constrained hopping model, there's exponentially many frozen states, and at least that number of states have to be paired. Because any product state, unless it happens to be invariant under X, which is not possible, right? You can't have a state that's invariant under flipping all spins, right? A product state. So those states will sort of be, there's at least that many, okay? And there's exponentially many of those. So it's kind of interesting. It's a little bit maybe of a curiosity, but it's kind of interesting that you can use those exponentially many subspaces to like encode information in some way. Would you want to do anything with it? Probably not, but an observation nonetheless. Good. That's all I wanted to say. Yes.
One question?